Hello, welcome back to Digital Circuits, and today we're going to be learning about transferring between schematics, equations, and truth tables, with equations as our sort of mediator. We will also learn about minterms and maxterms. I have an example drawn here for you guys, and it may have a gate that looks sort of unfamiliar. This gate over here is called the NAND gate. Logically, it's the combination of an AND gate and a NOT gate configured together. But in practice, it sort of has a different transistor formation, which is good to know, but it's not necessarily important for us in this video. Notably, there is a OR counterpart to the NAND gate, the NOR gate, and as you could have imagined, it's the combination of an OR gate and a NOT gate. With that aside, let's get into our example. Here we have a schematic drawn, and we want to derive an equation from it. When you're trying to derive an equation from a schematic, always go from left to right. Start with the inputs and try to arrive at the output one gate at a time. Let's start with this OR gate. It takes x1 and x2, two signals, as its input. Drawing this out in terms of the equation, let's start by writing z equals, and let's write x1 plus x2. This is a representation of our initial OR gate, and we can move on to our second gate, which is the AND gate that takes x3 and x4 signals as its input. Now, since it's an AND gate, it will be x3 times x4. So let's write that down in the equation. All right, next up, I'm sort of going to ignore the NOT gate that we have and move on to that NAND gate. And the reason I'm doing that is because the NOT gate just sort of inverts one of the signals and isn't really necessary to consider on its own. So for our inputs for this NOR gate, we have the output from our AND gate with x3 and x4. So we'll use that as one of the inputs. And the other input is the knotted version of the x2 signal. So we'll just do x2 complement, and we'll put all of that in brackets, and we'll complement it to sort of show the fact that it's a NOR gate. It's important to keep in mind that this complement is in the brackets, so what we're actually complementing is x2 prime, or x2 complement, times x3 times x4. So that's something important to keep in mind. And finally, let's move on to our final OR gate. Our final OR gate takes in that big expression on the right as an input, and it also takes in x1 plus x2 as an input. So simply by adding those together, we have our output z. And that is how we go from schematic to Boolean expression. All right, now let's go from Boolean expression to schematic. The best thing to do when drawing a schematic is to first write out all the signals. So here I'm writing x1, x2, x3, and x4. And I will start by analyzing the x1 plus x2 within the brackets, which means we have to add an OR gate. So here it is. I add an OR gate, and as some of you might have noticed, there's a complement on top of the brackets, meaning that we have to add a NOT gate to the output of our OR gate. And then we can start analyzing the rest of the circuit. Next up, we see that this entire expression is multiplied by x3. That means the output of this section that we have just drawn will be inputted into an AND gate with x3. So let's make that happen. Here it is. Now we see that the entirety of our circuit that we have just drawn is ORed or added to x4. So let's make that happen. And here we have it. We have our entire equation realized as a circuit, and the output to this circuit is z. All right, with that, we now know how to go from schematic to equation and equation to schematic. Let's now focus on going from equation to truth table and back. Here on the left, I have an equation drawn, and on the right, I have a truth table. Whenever you're going from equation to truth table, you want to write down all the possible combinations for the variables in your equation. In this case, I have two variables, meaning I have four possible combinations for inputs. All right. With that, let's find out what the output is for the first line of inputs. So we get 0 plus 0, and we're going to want to multiply that by 0 complement, and that's what z is. So 0 plus 0 is 0, and 0 complement is 1, and 0 times 1 gets us 0, so our output z is 0. Now let's focus on the second line. So for x1 we have 0, and for x2 we have 1. So we'll do 0 plus 1 in brackets, and we'll multiply that by 1 complement, and that equals z. So 0 plus 1 is 1, and 1 complement is 0. So our output ends up being 0. So write that down. Finally, let's do our third row. So we have 1 for x1 and 0 for x2. So we go 1 plus 0 times 0 complement equals z. So we get 1 times 1 equals z. And our output ends up being 1. Finally, let's do the fourth row. And for the fourth row, both x1 and x2 are 1. So we're going to do 1 plus 1 times 1 complement equals z. 1 plus 1 equals 1 times 0 equals z. And 1 times 0 is obviously 0. So our output is going to be 0. So the signal was only on when x1 was 1 and x2 was 0. Next, I will be showing you how to go from truth table to equation. This requires knowledge of minterms and maxterms, or SOP and POSs. And to fully understand these concepts, it requires a base level knowledge of binary number systems. I have a video linked in the description, so feel free to watch that if you're not familiar with them. Now I know what you're thinking. I already know what SOP is. That's what the Straw Hats used to beat Doflamingo. And you would be correct, but it's slightly different in digital circuits. I have a truth table drawn here, and I have the corresponding minterms drawn on the left-hand side. Now you might have noticed something. The numbering on the minterm actually corresponds to the binary number that the inputs represent. So what exactly do I mean by that? Let's examine the first row with M0. So M0 is obviously 0, and our three inputs are 0, 0, 0, and in binary, 0, 0, 0 is 0. In the second row, we have M1, which is 0, 0, 1. 0, 0, 1 in binary is 1. 0, 1, 0 in the third row, which is 2. We have 0, 1, 1 in the fourth row, which corresponds to 3, and so on and so forth. Now, I'm going to mark all the rows where the output is a 1. This is important for sum of products or minterms, as we only consider these rows. Now, I'm going to want to add all these minterms together, and this might not make sense at first, but you'll get it soon enough. So I'm going to add M2, M6, and M7, and that's going to equal my output. Once we have our equation written, we can start defining our minterms. I want to start by taking a look at the third row with M2, where our x1 input is a 0, our x2 input is a 1, and our x3 input is a 0. We're going to write x1 prime times x2 times x3 prime. Now you might have noticed something. If the input for that particular variable was a 0, we put a prime. If it was 1, we don't put a prime, and we multiply these three inputs. And we're going to want to add M6. Now let's take a look at the seventh row, and let's take a look at M6. We have that x1 does not have a prime. We have that x2 also does not have a prime, and we have that x3 has a prime because it's a 0. So we get x1 times x2 times x3 prime. And keep in mind, these are still the binary representation of these numbers. Now let's take a look at the M7 minterm, which is in line 8. So for this particular minterm, x1, x2, and x3 are all 1s, which means none of them have primes. So in our algebraic representation, we're going to want to write x1 times x2 times x3, and we're going to set all of that equal to z. Now this is why it's called a sum of products, because we basically take all of our products that make our output 1, and then we add them or use the OR function to make sure that if any of these products equal 1, then the output equals 1. This is important as they're the only products given in our truth table that make our output equal 1. Now you may have noticed that the equation we get from doing our minterms is pretty complicated. If you're not sure how to simplify this equation, I have a video up on Boolean algebra, which you can find in the description below. Alright, here's a new truth table with a new function. Let's now focus on the max terms. When focusing on the max terms, we want to look at all the outputs which return a 0. So let's write down our equation. We're going to want to write down M0, M1, and M4. You might have noticed that we use capitals for max terms and lowercase for minterms. And we're going to want to multiply those together and set it equal to our output. Now max terms are different compared to minterms in that when we have a 0, we're not going to put in a prime. And when we have a 1, we are going to put in a prime. This will make sense pretty soon. Now let's start writing down our equation. So for m0, we have x1 plus x2 plus x3, and we're going to want to put that in brackets and multiply it by x1 plus x2 plus x3 prime. And we're going to want to multiply that by our fourth max term, which is x1 prime plus x2 plus x3. And that's going to be our output. Now this is called a product of sums because you are compiling all of the rows, which make the output a 0, and you're multiplying them together because if even one of these ends up returning a 0, then the whole function ends up returning a 0. And you may have noticed that any other input combination returns a 1, which is what we want the function to do. Thank you for your support and have a great day.